Hello everyone. Here in last session there was a little mistake. I'll discuss the correction and then afterwards we'll go ahead with the further things. You can remember this particular figure wherein we are trying to discuss hydrostatic force on inclined submerged surfaces. So this is the surface actually, but how it is held is not this way, that is the plane is perpendicular to the horizontal or the plane is vertical in this case, but this is not the way how we are going to analyze. The plane is made inclined to the horizontal. The thickened blue thing is nothing but the same plate seen edgewise. As we have seen in earlier cases, so plate when it is held like this vertically is analyzed, but this is just to make understand how the plate is looking. When you look it from the top like that, this is how it looks. But in this particular case, when we say inclined submerged surface, it is held like this, making an angle of theta. Right, the surface area which is exposed to the liquid is A. Theta is the inclination made with vertical. With horizontal. Now I have considered a small elemental area dA. The force acting on that is dF. The force is given by the pressure intensity multiplied by the area dA. But pressure intensity is given by gamma into H, because gamma is the unit weight of the liquid, H is the height. Okay. So P is given by gamma into H. So I substitute in dF. P is gamma H dA. Then that F, if I want the total force which is acting on the whole area, F, that will be integrated. So integration gamma H dA. Gamma is a constant, that is a specific weight of the liquid is constant. Because of that it will be integration H dA, which is nothing but the dA multiplied by H is nothing but moment of area about this axis, which will be equal to the area multiplied by distance of centroid from the free surface HC, right? Distance of centroid from the free surface is HC. So that's why it becomes F equal to gamma AH bar. H bar, H bar, HC or X bar, all the notations are used for this. So what you should remember is, I have highlighted the equation. If you want the resultant force on the surface, it is the specific weight of the liquid multiplied by the area multiplied by distance of the centroid. You can just see here, distance of the centroid from the free surface. This diagram is for understanding purpose. This is not the actual situation. Actual situation is the plane is over here, the centroid is over here. The distance of the centroid from the free surface is HC or H bar or X bar, right? So that is what is to be multiplied so that you get the total force. Now from the geometry over here, one can write H bar or HC is equal to YC multiplied by sine theta. Similarly, CP or CP is the point where the total force which will be acting on there, that will be center of pressure. So HCP is the vertical distance. HCP is the vertical distance. Now if you want this again in this with the same triangle, if I indicate this distance as YP, so HCP becomes YP sine theta, and we know that moment of inertia about an axis perpendicular to this point A, perpendicular to the plane of whatever we are seeing, right? It is perpendicular axis, is equal to moment of inertia about this axis is equal to moment of inertia about centroidal axis, right? we have to, if we have to see it from that angle, then that axis becomes this required axis h. Moment of inertia about axis A will be like this, is equal to moment of inertia about centroidal axis, it will be like this, plus area multiplied by distance between the two axes, that is yc squared, a by c squared. So this we are going to use in further things. So here, by using Varignon's theorem, what is Varignon's theorem? Moment of resultant is equal to sum of moments of all the forces. Here all the forces in the sense df, such small forces for every dA they are there. So when we do df into y, that is df multiplied by its corresponding distance from here, right, from this axis or from this axis, right, this point, df into y integrated over the whole area should be equal to moment of the resultant force and its distance. Its distance we have given it as yp. So f into yp should be equal to integration of df into y. Now what is this f? F is gamma ah bar multiplied by yp is equal to integration. This df is nothing but p into dA, that is gamma h into dA, you can just see here, right, then multiplied by y. So this gamma is taken out, y is h is written as y sine theta, h is written as any h, if you take it will be y sine theta, that is substituted. Then what happens is this y becomes y squared, sine theta is there, dA. So integration y squared sine theta dA, again theta is not changing, because of that it can be taken out. Gamma sine theta is inside, outside, it's not a variable. So integration y squared dA, integration y squared dA, y is the distance and dA is the area multiplied by distance, so it is nothing but second moment of area about the axis there. That's why it is IA, moment of inertia about A. So this is gamma A h bar yp equal to gamma sine theta IA. Now gamma getting cancelled on both the sides, will be left with ah bar yp. Instead of yp I have written it as hcp by sine theta is equal to sine theta IA. So hcp can be written as, this becomes sine squared theta IA divided by all this ah bar. Now hcp, that is the depth of centroid, center of pressure, the depth of center of pressure, the point where the total force is acting, is equal to sine squared theta IA divided by ah bar. But IA, moment of inertia for this axis, is equal to moment of inertia for centroidal axis plus ayc squared. So I'll substitute for IA as Ig plus ayc squared divided by ah bar. Okay. Now, when I take this inside, right, what it gets is Ig sine squared theta, divided by ah bar plus this a into yc squared sine squared theta divided by once again ah bar. Now from this one can say that yc sine theta is nothing but h bar itself, so it will be h bar squared. So a cancels, h bar square, only h bar remains, because of that it is h bar, and this term remains as it is, Ig sine squared theta divided by ah bar. So hcp is given by h bar plus Ig divided by ah bar. This theta for 90 equal to sine theta becomes 1, because of that the equation gets transformed in this manner. So that is for vertical surface. for inclined surface, this highlighted quantity HCP is equal to h bar plus Ig sin squared theta divided by h bar is the equation. Okay, this correction can be taken. We'll continue with the next session. Yes, hello everyone. So we'll continue our discussion on hydrostatic forces on immersed surfaces. We'll solve a good number of problems in this session. We have already discussed these things, that is force and center of pressure on vertically immersed surface. Just once again, a different way of doing the same thing. Quickly we'll recap. I have considered vertical surface, and then when you look at it in this manner, it looks like an edge here. The total force is represented by big F, and the point where that total force is acting is represented as Cp, or center of pressure. The depth of center of pressure is represented by HCP or YCP. The centroid of the figure is represented as C, centroid, and the depth of centroid is represented as x bar. Earlier we used to call it as HC or YC or x bar. In vertical surfaces, Y is vertical only, right? Here elemental area dA is considered, which is at a depth of Y, and the pressure at depth Y is gamma into Y. So this small force which is acting on this elemental area is dF, which is given by the pressure intensity multiplied by dA. Pressure is given by gamma into Y, so gamma Y dA dF. But if we want force, we have to integrate this expression gamma Y dA. But Y dA is nothing but moment of area, because area multiplied with the distance, that is moment of area about AB. If I put gamma outside and consider only integration Y dA, it is moment of all the area that is considered. So because of that, it will become F equal to gamma into AX bar, because integration of Y dA is the total moment of the area. So that is given by simply area, total area multiplied by its centroidal distance x bar or h bar. So that is what is the expression. Earlier also we have seen this. Maybe we had called it as gamma A h bar. H bar or x bar remains the same. It is depth of centroid from the free surface. That is what is to be remembered. Okay, next, here you can just see here, that is the surface I am talking about. Generally we draw the diagram this way more, right? But we want to see what exactly the surface is. It is like this. So in case of vertical surface, whether you draw it this way or this way, it hardly matters, because the depth of centroid, the depth of center of pressure, they all remain the same, whether you are looking this way and then centroid, or looking at this way and its centroidal depth, it is one and the same. Only thing is, when the surface is not vertical, then it creates a problem. We'll see that in later stage. So here, for sake of YCP, what we use is Marignon's theorem, or law of moments, or principle of moments. What it states is moment of the force is equal to moment sum of all the forces. That is what it is. So the resultant force F multiplied by its distance YCP is equal to the small force dF multiplied by Y, but integrated over the whole area. But dF is equal to gamma Y dA. That I'll substitute here and simplify. Gamma remains outside, so it becomes integration y squared dA. Y squared dA. About AB, it is moment of inertia. So if I simplify, gamma AX bar or gamma AH bar YCP is equal to gamma multiplied by AB. I'll write it as IZ plus AX bar squared, because moment of inertia about an axis AB is equal to moment of inertia about centroidal axis multiplied by area into distance squared by parallel axis theorem. So here YCP will be written as, if I take AX bar below, here there will be X bar left, and this will be Iz by AX bar. That is the expression. Here what one should understand is, Iz, moment of inertia, cannot be negative, area cannot be negative, X bar cannot be negative. It's all positive. So this plus can never be negative. Because of that, we can say that the center of pressure is slightly more than the depth of centroid. Means here you can see that centroidal depth and YCP is slightly more. This is always positive quantity. So always YCP is greater than X bar or Y bar or HC or H bar, whatever. It is more than the depth of centroid. That is what the point is. Okay, here there is an inclined surface. You can just have a look. That is what I mean. You can just see here the axis OO dashed is perpendicular to the surface. But if I look from the top, means if I try to look from there, how it looks is, it looks like this. The axis looks like a line, and then the surface taken is something like that. But when you see it from the side, it looks in this manner. So here the plane is making an angle theta, and its centroidal distance I have called it as X bar. The point where the resultant force is acting is known as HCP, right? Now those corresponding distances, now general distance h and the df as the force, which is equal to dA multiplied by h, gamma h, right? df is equal to p into multiplied by area, p dA, right? P is given by gamma into h. Okay, now this inclined distance from point OO dashed to this, we have called it as y. The centroidal distance from OO dashed is called as y bar. The center of pressure distance from OO dashed is called as YCP. So because of this right angle triangle, every time I can write sine theta equal to opposite side upon hypotenuse, h by y, or X bar by Y bar, or HCP divided by YCP. So that is what is sine theta expression. Now further, moment of inertia about OO dashed axis perpendicular to this, is given by y square dA, where y is the general distance, dA is the elemental area. Here it is shown as a strip. IO is equal to IZ plus AY squared, A bar squared or X bar squared, right? And not X bar, Y bar squared, that is distance of centroid square. Now P is equal to gamma H, dF is equal to P into dA, gamma H dA. Now dF will be equal to gamma into H is given by Y sin theta dA. So integrating on both sides, gamma sin theta remains constant, integration y dA. It is again moment of area, because of that gamma sin theta multiplied by AY bar or AX bar rather. Y bar is this distance, inclined distance y bar I have called it as gamma A y bar sin theta. So because of that, F becomes gamma AX bar, because y bar sin theta is X bar. Now using Varignon's theorem, that is sum of moments of all the force, resultant force is equal to sum of moment of all the forces. That is what it is. Now df, small elemental force, multiplied by y, its distance, is equal to elemental moment over here. Now sigma mo, if I want to do all those summed up sigma mo, you have to integrate this YdA over the whole area. Now df is given by gamma y sin theta dA. Because of that, this ycp multiplied by f into ycp f into is equal to gamma sin theta outside integration y square dA. So here it becomes gamma sin theta fine, this becomes I naught. Then f is gamma ax bar, ycp is hcp by sin theta. This sin theta goes there, and I naught is equal to Ig plus a bar y squared. Y bar squared. Now this is by parallel axis theorem. I naught can be replaced by Ig plus a bar a into y bar squared. Now from this expression, HCP can be simplified as sin squared theta divided by ax bar in the bracket Ig plus a into y bar squared. If I simplify, so what I get here is, if I go inside, what you will be getting is, look at that. I have written y bar sin squared theta as x bar. So ax bar square divided by ax bar, that becomes x bar. And then Ig sin squared theta ax bar remains as Ig sin squared theta ax bar. Here there was a bit of a trouble. I think I can understand that while studying this, there shouldn't be any difficulty. Okay. Now application of whatever we have studied. So very simple problem with that rectangle, which is 2 meter by 3 meter in height, and this is the axis, or this is the horizontal free surface, both. Now the vertical lamina is having a distance 2.5 from that end, and another 3 meters is nothing but this end. So what is your opinion about the force of that? Now if I go by in a usual manner, we need to know moment of inertia about centroidal axis as well as moment of inertia about that axis. Now moment of inertia about this axis, that is what is the point of discussion, 2 into 3 cube by 12. It is not 3 into 2 cube by 12. Moment of inertia about this axis, horizontal axis, is 2 into 3 cube by 12. If we want moment of inertia about this axis, then it would have been 3 into 2 cube by 12. But in this case, we want moment of inertia about this axis. That's why it will be 2 into 3 cube by 12, 4.5. I naught will be equal to 4.5 plus a bar squared, that is 3 into 2 into 4 squared. Then if you calculate, I naught will be equal to 100.54, whereas I bar becomes only 4.5. Huge difference is there. Okay, now this is just calculation of moment of inertia. Now how it is used in a problem of force calculation. Now look here, that is the edgewise view of a plane. But if it is seen from the front, what you will have is this way, look, right? Now the upper edge is 1 meter below the free surface, this is 3 meter. So area of the surface becomes 2 by 3, 6 meters square. Centroid is over there at a distance of 1.5 meters. So x bar becomes 1 plus 1.5, that is 2.5. Force is given by gamma x bar. Gamma is 9.81, area is 6, x bar is 2.5, so it becomes 147.15 kilonewton. HCP is given by the formula x bar plus Ig sin square theta divided by x bar. X bar in this case we have worked out, it is 2.5 plus Ig, again Ig is 2 into 3 cube by 12, 2 into 3 cube by 12, which is 4.5, multiplied by sin squared theta is 1 because it is sin 90, and divided by sin theta is equal to 1 squared is 1, and divided by A is area into x bar is 2.5. X bar is 2.5. Now if you simplify all this, you will be getting 2.8 meters. So 2.8 meters is the center of pressure, whereas x bar is 2.5 meters, that is position of centroid. Position of the total force will be slightly below the centroid. That's what the point is. Okay, here a vertical rectangular gate 2 meter wide and 2.5 meter high is subjected to water pressure on one side. The water surface being at the top of the gate is hinged at the bottom and is held by a horizontal chain at the top. Calculate the tension. Okay, figure will be given to you. Here we are going to discuss next problem. I'll read the problem for you. A vertical rectangular gate 2 meter wide and 2.5 meter high. It is vertical. This is edge view. If you look exactly at the front, it looks 2 meter wide, 2.5 meter deep. On one side, the water surface being at the top of the gate, means the surface of water is matching with the edge of the edge of the gate. The gate is hinged at the bottom and is held by a horizontal chain at the top. Calculate the tension in the hinge. So arrangement is such that this particular edge is hinged with a hinge there, so that it is free to move this that way. There is water here, because of that the pressure pushes it that way, but this is held by a force P with a chain at the top. Now what is the P required so that this is kept vertical? That is what the problem is. So if I show the forces acting on this, the same free body diagram, the total force at the hinge is shown as R. The applied force to keep the thing in vertical position P, and the resultant force which is acting because of the standing water is F, and the location where it will be acting from the top edge free surface is HCP, and that is in this case it is 2.5 by 3, because centroidal distance is 2.5 by 2, but this distance is 2/3 of 2.5, that is 1.67, because resultant force from the bottom is given by 2.5 by 3, 0.8333, 2.5 minus 0.833, that is 1.67. Anyway, that is just position of the resultant force. Now what we want is P. So here it is done. The force F is given by gamma A x bar. A is 2 into 2.5. Gamma is water, 9.8 kilonewton, multiplied by A, 2 into 2.5. X bar or H bar is nothing but position of centroid from the free surface, that is 1.25. So F becomes 61.25. This F is 61.25. HCP is given by x bar plus Ig Ax bar, Ig sin squared theta, but theta is 90, because of that it is simply Ig. So Ig is here there is a centroid. Ig is moment of inertia about an axis like that. It will be 2 into 2.5 cubed by 12, 2.604. So I'll substitute for HCP. X bar is 1.25 plus 2.604 divided by area, that is 5, multiplied by x bar is 1.25. So if I simplify, it will be HCP is equal to 1.67 by formula also. But if the surface of water is joining the edge of the plane lamina, then directly one can put it as, from the bottom it is h by 3, from the top it will be 2/3 of h. Now for equilibrium of all these forces, moment summation about n equal to 0. So F into 0.833 clockwise moment, P into this whole 2.5 equal to 0. So F is 61.25 into 0.833 clockwise moment. Anti-clockwise moment is the P into 2.5 equal to 0. So the force P, which is acting on the edge of the gate to hold it in vertical position, is given by 20.42 kilonewtons. Okay. Here is one more. An equilateral triangular plate of 6 meter side. It's a triangular side of triangle of a side, equilateral triangle is all the edges are same. So this is 6, this is 6, this is also 6, this angle is 60, this angle is 60, this angle is also 60. That is what is equilateral triangle. Is immersed in water with its base at 2.5 meter below the free surface. The apex of the plate is 9 meters below the free surface. Now base is, look at that, in water with its base as 5 meters. So if the base is at 5 meter, the water should be somewhere there at 1 meter, but it is not so. What is said is, with its base at 5 meter below the free surface and the apex of the plate is 9 meters below the surface. Means it is not like this. Maybe it is like that, so that this is free surface, so that this distance is now 5 meter. Now here what happens is, this particular distance we'll have to calculate 6 sine 60, but it is said that this is 9 meter below. So because of that, it may not be vertically immersed also, right? So such problems you have to imagine the figure properly, then afterwards analysis starts. Now determine the total pressure on the plate and the location of the center of pressure below the free surface. Now here it is like this. You can just see here, this is the plate. The plate is inclined, the plane is inclined at an angle theta, we don't know, but what the data is given is, this top edge is 5 meter below and the bottom edge or apex is 9 meters below. So 5 meter and 9 meter, so this distance becomes 4 meters. This becomes 4 meters. This distance will be 6 sine 60, right? See, when you look at the triangle from this angle, exactly from that way, it looks like this: 6 meter, this is 6 meter, this is 6 meter, but this bottom one of the edge is parallel to the horizontal, and it is said that it is 5 meters below. That's why the diagram is like this. Okay, here this distance will be 6 sine 60, because 60 is that angle. The opposite side of triangle, if I try to analyze this triangle, that is with a 90 degrees there, it is a right angle triangle. So hypotenuse is 6, angle 60, opposite side will be 6 sine 60, that is 5.2 meters. So this distance is 5.2. The angle theta we don't know, but this is 4 meters. So in this triangle, angle can be calculated, right? So how do we do that? This edge, that is this particular point, if you look at the point of centroid, which is h by 3, that is 6 by 3. H by 3 is not 6 by 3, 5.2 by 3 is 1.733 meters. So this is equal to 1.733. So here the triangle, a small piece of a triangle, has to be analyzed for theta, but for that I have calculated sine theta as 4 divided by 5.2. fine. So this whole triangle, when you take sine theta is equal to, that theta is equal to sine theta equal to opposite side upon hypotenuse, 4 by 5.2, that is theta equal to 50.3. And then afterwards this x bar, that is position of centroid from the free surface, if you want, we want this additional 1.733 sine theta, because in this triangle theta is there, hypotenuse is already 1.733. So sine theta becomes 1.733, sine theta becomes 1.33. So 1.33 plus 5, that will be 6.33 becomes x bar. Okay. Now this area of a triangle is equal to 6 into height by 2, 6 into 5.2 by 2. Gamma is water, gamma A, x bar is 6.33. Because of that, the resultant force acting on the triangular plate will be 969.3 kilonewtons, that is F. Now if I want to calculate HCP, I need x bar plus Ig sin squared theta divided by Ax. Ig I have to calculate. Centroid is here, moment of inertia parallel to the base axis. This one is Ig, which is given by BH cubed by 36. So 6 into 5.2 cube by 36. So Ig becomes 23.43. I substitute all that. Theta is already worked out, area is worked out. If I substitute and simplify, obviously it is simple to work out with calculator. 6.33, 23.43 sine squared theta, 50.3 divided by area 15.6, x bar is 6.33, is equal to, if I simplify, you'll be getting 6.333. This whole expression is adding to only 0.1, so it becomes 6.473 meter from the top. That is what is the problem. Okay, thank you. We'll stop here.